Okay. So what did we talk about last time? We started talking about how we can use the knowledge that you learned about wave propagation and resonance in non-destructive evaluation. So just to review the things we talked about, let's look at this quiz that we just did. So this is a true transmission test, similar to what you did in the lab. P-wave transducers, and I'm telling you that the wavelength is smaller than the dimension, meaning that we are dealing with 3D wave propagation. And if you have a length of d, and if you send in your pulse, basically when you put the two transducers in contact, you get T0. When you place them on the sample, as you did in the lab, you get T1. The question is, what happens, what do you expect to see if this sample is 2 times longer? I guess the velocity is kind of easy to explain. So if we consider the velocity for the case when the sample is 2 times longer, so the length would be 2d, where do we see T2? What do you expect?
2 times.
It should be about 2 times larger than T1, correct? And this is easy to see because we are saying it's the same material. So when the distance is basically time of flight. I write time of flight. I want you to get used to this notation. Time of flight would be distance over velocity. And of course, since it's the same material, the velocity stays the same. So if you double the distance, the time of flight should be also doubled. How about amplitude? Last time we talked about several mechanisms of attenuation. Let's discuss this in the class. Do you remember what we talked about? What were these 3 mechanisms of? How many did we have? Right. So we talked about 3 different mechanisms of attenuation. This was actually originally I wanted to give you this as a quiz, just that you write down what are the different mechanisms of attenuation and explain it. And I thought, it's better to make it tangible, to you apply it to see what that knowledge, how it translates to measurement. So we, as Tiffany pointed out, we have intrinsic damping. This comes from material. It has microscopic origins, and it comes from the material itself. Some material are more attenuating than the other. For example, if the material is viscoelastic, you have certain damping behavior, just because the material is like that. And then the second one was geometric spreading. So can someone else other than Tiffany remind us about geometric spreading? Why do we have that? Any ideas? Any discussion? So let's look at this figure a little bit more closely. I was hoping that you looked at this a little bit carefully at home, and we can do it now together. So here we talked about we have geometric spreading because the energy, you have the same amount of energy as the wave propagates. Let's say P wave in this case, the wave front is, what shape does it have? Look at this figure. It's a spherical. So you have the same amount of energy and it spreads over, in this case, half a sphere, and as you go, these spheres become larger and larger, and because of that, the amplitude has to become smaller. If you look here, there is the geometrical damping law. So for shear and P wave, inside the bulk of the material, the amplitude changes proportional to 1 over distance. That's what it means, r minus 1. This is easy to show. I saw that Ji Young has kind of you try to quantify this, and you had the right idea, but why it is 1 over r? Take 30 seconds, think about this. Why the geometrical spreading of P and S wave in the bulk of the material, based on what I told you? It's very simple. Why is it proportional to 1 over r? I can give you hints.
The surface, the area, because it is running on an area.
Area. So what area is it?
It's
Forget about the surface right now. If it is just, if you have a source inside the material, the area is a sphere, right?
Mm-hmm.
What's the how do we calculate the surface of a sphere if the radius is r? 4 pi r squared, right? I think Jian had it even written this down. Okay, now, how do we relate this to the attenuation? So remember what I said earlier. So why does it attenuate? Because you have a source of energy. Let's say you have energy E0 at time T0. And this stays the same at the other times. So you always have, this is constant. And energy is proportional to
velocity squared.
velocity. Hi, Shushu. Energy is, so Shushu, energy is proportional to
wavelengths.
sit down. This was just a joke. Is proportional to amplitude squared. Remember when we were talking about the spectra, I told you, when we have power, bandwidths, remember always energy is proportional to a square root of amplitude. So now you should see what's happening. So if we go from one location to the other, the area is changing proportional to r squared, and the energy is proportional to amplitude squared. So the amplitude will be proportional to 1 over r. Correct? So now going back to our quiz. So we have geometric spreading, and since it becomes double, so you kind of expect that just because of geometric spreading, your A2 would be 1/2 of A1. You agree? Right? Approximately. This is not, we don't have a half a space. I know all those other stuff, but approximately this is what you get. Now, just because of geometric spreading, what was the third mechanism Tiffany told us about? Someone else other than Tiffany? What's the third mechanism of spreading? Attenuation, sorry. Scattering. So why does a scattering happen? Why does it happen? Do we have a scattering, let's say, in a purely elastic, homogeneous material? No. So why do we have a scattering? Why do we have a scattering in concrete?
We have averages.
Right. We have heterogeneities. Whenever you have heterogeneities inside the material, we have a scattering. But there is some other important parameter when we talk about a scattering, and that is remember the experiments you did when you changed the frequency? What were you changing really? Velocity you measured was pretty much the same. All of you in your reports wrote that, the velocity hasn't changed much. When you change the frequency and the velocity is not changing much, what are you changing really? Wavelengths, thank you. So if you have wavelengths is velocity over frequency. So if the velocity is the same and you are changing the frequency, then the wavelength is changing. And scattering is controlled not by wavelengths by itself. So just saying wavelengths is not enough. What controls the scattering? What is it?
The length between averages.
The relative relationship between wavelengths of the ultrasonic energy and the wave scale, the length scale of heterogeneities, in case of concrete aggregates, right? So this is what we talked about last time. Now, going back to our quiz, I guess we all agree that, because of geometric spreading, did I give you one copy, Shushu? Yeah. So because of geometric spreading, if there was nothing else happening, the amplitude would be halved. Now, if we have more material, you also have more intrinsic damping, right? You also have more scattering. So at the end, we expect to see that A2 would be smaller, probably much smaller than 1/2 of A1. Now, quantification of those two is another matter, so we don't want to now spend time on it, but this is what it is. Okay, so this is a good kind of review of what we were talking about last time. Another thing we talked about was honeycombing, how we used some of these principles to find honeycombing. Does anyone want to give me what you remember from last time, the two methods we used to find honeycombing? So that's a measure of attenuation. And then the second one, we also looked at ultrasonic testing. And in ultrasonic, what parameter did we use?
With velocity and attenuation.
Right. We looked at velocity and we saw that the velocity is slightly smaller. Now the last thing we talked about last time was about what happens if you have material which has a population of cracks inside. How does it affect wave velocity? Now, I formulated this now into a second part of this quiz that I want us to do right now together. So the question is, how much does the wave velocity change if you damage the sample, the original sample? That means the length is d, and you have a density of penny-shaped cracks. And I give you this density parameter to be 0.15. Let's look back at this last topic that we touched last time. And recall what we talked about. So which page is it? This is rather an important topic for a lot of you, especially my own students. So I told you that using principles of thermodynamics, it's possible to find analytical relationships describing what happens to the elastic modulus if a material, elastic isotropic, has a collection of cracks. And these are the two relationships. So this means that if you have a population of cracks of density rho, which we define the density rho to be 1 over V, that's the volume of the representative element, and then the summation of the cubes of the radius of your cracks, you can calculate the effective modulus of your material, given that. So now,
I'm sorry, what is it? So V is the volume of that.
yes. So
And Li is the.
yeah. So Li is like half the length or the radius of a penny-shaped crack. So now let's use this formulation and try to see what happens if you have a certain population of cracks inside your material. I keep going to this. Okay, so I have given you rho. We need to assume some value for Poisson's ratio for concrete. What would be a good value?
0.19.
Let's say 0.2 or 0.25 would be a nice number. Let's go with 0.25. So we have rho. All you have to do is you have to calculate what would be the effective modulus compared to E0. Please use the formula in your notes. Take your calculator and calculate it. We consider this to be dry cracks. So we don't have any liquid inside the crack. one?
Yeah, I think so.
So it's a dry crack. That means that delta over 1 plus delta, you can take it to be 1. Anyone has a number?
0.791.
Okay, let's get more than 1. Point.
1.26. That's
This is what I want, the effective.
And you have one power.
1.536.
Again, the similar answer is shown.
You have the same? Okay,
Yeah.
is it
Yeah.
0.791?
0.791.
How about G? You have it? How much?
Almost the same. 0.78.
8,
6.
7, 8, 7.
7.
Okay. Now with this, can you answer this question? What would be the change in velocity? So the velocity, the original sample, if we call this V0 for the original one, the velocity was d over t1 minus t0. And you know that the velocity is proportional to a square root of e. However, this is three-dimensional, so there is also Poisson's ratio. If we kind of assume that the Poisson's ratio is not changing that much, you can say that, but because we have both E and G, you can even see how Poisson's ratio has changed. So you can be as accurate as you want. But let's say if we just consider this, you can say that the V in the second scenario compared to the first scenario would be proportional to basically what you have. So what would be the square root of this?
It's 9.89.
Thank you. 0.89. So if you have a population of cracks which is not negligible, remember I showed you that even a smaller number, 0.125, it's not negligible. It's still a lot of cracks. If you have this much crack, 0.15, the change in velocity is about 10%, right? So it's not much. You have to have a very accurate system to be able to measure this accurately and to be able to say that you have this kind of, you have a population of cracks inside the material. Does it make sense? Okay, so this is how these formulations can be used. Now, of course, we are not the first people who wanted to relate the wave velocity to the damage in material. Here, you have listed a list of people who, from 1970s, they tried somewhat to relate the wave velocity to the amount of damage that you are seeing in material. Most of these experiments look like what I'm showing you here. You are loading a sample. Here uniaxially, you are compressing the sample, and then you have a pair of transducers in true transmission, and you are measuring p-wave velocity. So here you see the propagation direction is from S to R, sender to receiver, and this little arrow here, it's particle displacement or velocity. So you know that we are talking about p-wave velocity. Now the collective results of these experiments were something that you can see here. The x-axis is a stress-strength ratio going from 0 to 1, meaning that at 1, the sample fails in compression. So you are increasing the load, and you are looking at variation in velocity. This is like v minus v0. Yeah, it starts from 1. So you are basically, this is normalized with respect to 1. It's not like that. Okay, so you start from 100%, nothing is changing, right? And then it changes a little bit, and it changes more for coarse concrete rather than medium concrete. And you see that at about 80% of the stress-strength ratio here, the change is 5%. So this can tell you that what we calculated before with crack density 0.15, that was a lot of crack. So even when you are almost about to fail, the change in velocity is very, very small. Now, you can measure the velocity in different directions. So this is some experiments we did in the institute I was working. So we instrumented a concrete sample, as you can see, with different things: acoustic emission, ultrasonic wave velocity, surface wave velocity, all sorts of, as you can see, it's completely instrumented. And we also had strain gauges to measure the strain. And what we did was not only measuring the velocity perpendicular to the load, but also parallel. So we had sensors in the load plates that also could measure the velocity in the direction of the load. And this is how the results look like. So here you see the waveforms. So you can see that as you are increasing the load, the arrival time up to a certain point is not really changing much, and then at some point it arrives much later, meaning that the velocity has decreased substantially. When we are measuring parallel to the load, something interesting happened. If you are looking at the figure, what do you see? So you see the increasing load, the arrow, and you see the waveforms as you are increasing the load. What's happening to the velocity?
It's kind of decreasing.
Decreasing? The waves are arriving actually earlier, right?
Really hard, yeah.
So compare the two. Here is similar to the old measurements that other people had also done. So you can see that in the beginning it's kind of constant, and then at some point the arrivals are later. Now you have done experiments in the lab. I hope that you can see what I'm talking about. Here, when we measure the wave velocities parallel to the load, the arrivals are earlier, meaning that the velocity is actually increasing. How can that happen?
Because the material is more compacted and the velocity is quicker, it's faster. Or the cracks inside is more closed than open.
It's not damaged. This concrete was not damaged. So now just focus on the purple plots. The black plots are something else I haven't taught you about. So if we do a lot of these experiments and have the nice error bars, etc., if we look at perpendicular to the load, basically we get what everyone else had got, that the velocity stays pretty much constant, and at some point it starts to go gradually down, and towards the end it goes very sharply down. And when we measure parallel to the load, the velocity kind of goes up a little bit, and then towards the end it goes sharply down. So this change of velocity, so the point I want to make here is that the velocity changes with the presence of cracks, pores, etc. But the stress also changes the velocity in the type of material we are interested in concrete and rocks. So the change in velocity with the stress is called acousto-elasticity. In rocks, this is very important because in situ, the rocks always have confining pressure. So the velocity may just change because of different pressure. You don't even have to have cracks or anything else inside. So if you want to analyze the curves that we got, ignore this parallel and perpendicular because this is a little bit different kind of measurement. But just conceptually, this is what's happening. In the beginning of the loading, the velocity was actually increasing with stress. This is when we don't have much macro crackings, we don't have much damage, and what is in place, what controls this behavior is acousto-elasticity. And then, after a while, you start having damage inside. And then you have two competing mechanisms. From one hand, acousto-elasticity wants to increase the velocity, but remember, if you have cracks, the velocity goes down. So this competition results in having this kind of plateau. And then after a while, the amount of cracking becomes so much that acousto-elasticity is not in place anymore, and then the velocity decreases. We measured in concrete different kinds of waves, different materials, different configuration. We always saw this kind of trend, always. Yes.
So you're saying that as our stress increases, our velocity will increase up to a certain threshold, and that threshold is defined. What is this 30%?
This is 30% of the maximum failure. So when you are up to about 30% of the maximum load that you can reach at failure, so when you are still in this elastic regime pretty much, you have acousto-elasticity.
Okay.
And then it kind of, you still have acousto-elasticity, but the slope becomes smaller, reaches a plateau, and then you start seeing damage.
Okay, so the whole concept of acousto-elasticity, of your velocity increasing as your stress increases, is only true up to 60% of your
Right.
failure.
Right.
And then after that, the mechanism isn't acousto-elasticity. It's just
Micro cracking and acousto-elasticity, then they both are
they're
in
both
play.
still occurring, but now we're starting to have micro cracking.
Right, because
Okay.
you are creating damage after
So there's still
such
the
a
acousto-elasticity, but the introduction of these micro cracks is slowing it down.
right.
Okay.
Material also is not elastic anymore, so you can't talk about acousto-elasticity much. I'm kind of motivating. I want to teach you why there is this linear relationship. So I'm kind of first showing you the evidence and then formulas. This is the plan today. And then, actually, what happened was we were kind of the first people who observed this in this concrete. The first time I presented the results, the research group head told me, this is just error. This cannot happen. Like people in non-destructive evaluation of concrete, they were not aware of this phenomenon. However, when I looked into literature on rocks, people have done this from 1990s. And since rocks and concretes are very close to each other, then we were confident that everything is okay. And actually, we presented this exact same paper. So Sayers, he did a variety of measurements on Berea sandstone, and you can see the results. So if you want to compare our results parallel to the load, we have to look at these components. So here, the loading is along axis 3. And when we say V33, it means that we are measuring in direction 3, and the particle displacement is also in direction 3. And you can see that they are getting very, very similar results. Now, before developing this theoretically, let me show you some really cool experiments that we did afterwards. So this is actually my first PhD student work. So what we did was we picked really, really large samples. This sample is 1 meter tall, that's 3 feet, 40 by 60 centimeter. This is a huge piece of concrete. And we loaded this in different ways and fashions. And then we used several sensors, including the one I'm showing you is, we used an actuator as a source in the middle. And then using a laser vibrometer, standing few meters from the sample, we actually measured the surface wave velocity on the surface of this specimen. But not only at one location, but we measured the velocity every 10 degrees on the surface of the sample. So we wanted to see, the idea was to see the anisotropy that is caused by stress in concrete non-destructively. Basically trying to map a stress in material without having a strain gauge or without having any information, just from a velocity measurement. And this was very successful. So this is how, in the beginning, if we don't have any load, if you normalize, basically you have the same velocity everywhere. That's why you see a circle. Please ask me questions if this is a little bit complicated. Since I've done it, I can answer all the questions. Now, we have started loading the sample. This is at 25%. So what is happening is that the velocity along the axis of the load is increasing. That's why the red circle is changing to an ellipse.
Say that again.
So the red is the state, the stress-free state, when there was nothing. We normalize everything, we get a circle.
What is the simplifying?
It's velocity with theta. So we are measuring velocity and 360 degrees over a really large sample, really
so it's
huge.
the velocity before you apply the measurement.
Right, it's normalized, so it's all one. So this is like the beginning, okay? And then you start stressing the sample. And because you are stressing the sample, you are breaking the anisotropy. So one direction becomes stressed. You know what so you have a stress in one direction, it's uniaxial. So because you have a stress in that direction, the velocity is increasing, as you can see. So the circle is changing to an ellipse. Now, if you increase the stress, this becomes larger. Pay attention that the circle doesn't become a larger circle. This is completely anisotropic. In the direction of the load, the changes are much larger than perpendicular. This is what we wanted to study with this setup. And then here. Now, if you go above, let's say 50%, then you start having cracking. So when we go from 50 to 75, you see that not much is happening. And of course, just before failure, the whole thing shrinks. But now when it shrinks a lot more perpendicular to the loading because of all the cracks that you have parallel to the load created, and it shrinks like that. It was a very hard set of measurements to do, but I think it is very cool. No one else had done it, so it was a really nice thing to see. So one application of this kind of measurement is, for example, in pre-stress members, if you want to see that you have lost pre-stressing. And there is no way to find out right now. Exactly. If it is under stress, you should measure a different velocity than when it is not under stress. So that's one. Another thing is just to be conscious of that stress also changes the velocity. You saw that the change that you measure in velocity because of damage is not that much. So if you have a building, or if you have a bridge, or if you have anything that you are measuring, mapping the velocity over, some of these changes may be just because of the confining pressure that you are applying on your material. In rocks, this is kind of a well-known thing. People know that. But it took me 1.5 years, so people didn't even believe. Like, you had to really show them. So we did acoustic emission next to it. You can see when you are starting to have a lot of events in acoustic emission, that's when the velocity starts to drop. I didn't include that here, but it is in our papers. So we basically proved to the community that really this is also happening in concrete, and it is significant. You can't just ignore it. Now, with all the fun and excitement, why this is happening? Because something that you could have asked me was, wait a minute, you told us the velocity is in 1D square root of E over rho, and in 3D is a square root of M over rho, which M is, what is M?
Lambda plus 2G.
I'm sorry?
Lambda plus 2G.
What did we call M? That's correct. Constrained modulus. Constrained modulus. This you have to know. If you wake up, someone asks you, you have to know. This is a constrained modulus. So in 1D and 3D, we have two different modulus. Now, you could have asked me, like everyone else did when I first presented these results, wait a minute, the velocity is only a function of elastic modulus and density. How come you are telling us that the velocity is changing with the stress? It's a legitimate question, right? So, what is the trick here? Why don't we see anything about the stress in these expressions?
Because elasticity is a function of the stress.
Because?
Elasticity is a function of stress.
Right. Because what assumptions did we make to get those equations, remember? What assumption did we make about the material? The material is linear elastic. Of course, what we got is independent of a stress. That's why. But in reality, is when you apply a external strain, the material has nonlinearity. So acousto-elasticity is a manifestation of nonlinearity. I have to tell you also that in a steel, after we did these experiments, I learned about actually acousto-elasticity a lot more. And in 1950s, in a steel, people already knew that there is acousto-elasticity. So it's kind of a, I would say, standard measurement in steel to go and measure the velocity and relate it to a stress. People know this in metallic materials. But in rocks, it was 1990s, and this was a decade later in concrete. Anyway, so let's, I want to show you why we have this relationship, and more than that, why the relationship between velocity and strain is kind of linear. And what does that mean? So we need to kind of review a few things before doing that. We focus on this small problem that I also showed you, that we have uniaxial compression. So this is a uniaxial compression. We are applying a strain U1 or UX. I've used X and 1 interchangeably, X, Y, Z. And what we are looking at is p-wave velocity V11. Remember, 1 refers to the propagation direction, the other one, it refers to the particle displacement. For example, if I had a shear, vertically polarized shear, what would be the notation? So if instead of p-wave, we were studying vertically polarized shear wave, SV. V22, any other suggestions? V21. Suggestions?
You said the first number is related to the wave propagation.
Propagation. The second one, the direction of the propagation. The second one is the particle displacement. V12, exactly. So you have the idea. So 2,2 would not be correct, right? 2,2 is when you have the propagation direction in 2,2. It is if I had two p-wave transducers in this direction, vertical, looking at the thickness.
The first number is 1.
So if it was SV, it would be V1, 2 with this notation, right?
I don't understand the first number.
The propagation direction. So it's going from, this is the pulse, it's going from left to the right. So the propagation is aligned with axis 1 or axis X.
So it doesn't matter that it's a shear wave?
Yeah, so the number 2 tells you that the particle motion is in this direction. That's why how we know it is shear wave. Let me show you this one on rocks again. So this is what you are seeing here. these numbers, so when they are not the same, you are talking about shear waves, right? If they are the same, they are compressional waves. Okay, so now, is everyone familiar with tensor notation in continuum mechanics? A little bit? A little bit. Okay. Try to make this as easy as possible, but please be with me and pay attention. Something very important in the context of acousto-elasticity, also later on linear acoustics, is this concept of energy density. Energy density is nothing else but energy per unit volume. Okay, so if we have force versus displacement, if you look at the area underneath, that would be energy. If we have a stress versus a strain, if you look at the area beneath the curve, that is energy density. You should have seen this in other courses or other contexts. Convinced? No? So everyone agrees with me that if we have force and displacement here, and let's say your favorite linear elastic curve, if I look at this area underneath, this is energy. Yes?
Yeah.
So this energy, if everything is linear elastic, is what 1/2, let's say, F times delta, something like that. Okay, so this is energy. Now, what happens if I change this to sigma and this epsilon? That means I'm dividing this by A, dividing this by L. Isn't it as if I'm dividing this by volume? Very simply put, right? So energy density is the area underneath a stress-strain curve, basically, pretty much. So, yeah, we can use this actually here. If this was linear, let's say we had here K or E, however you like it. So this would be, the energy density would be 1/2 sigma epsilon, and then I would replace sigma by K epsilon. For reasons that I'll tell you in a second, I write it epsilon K. This is nothing else by sigma. You agree with me? This is familiar, right? Now, in the more general case, we write the energy density, which is nothing else by energy per unit volume, 1/2 summation of, so this is now a strain, and that's the elastic tensor. You don't need to know everything about this particular, this is just preparation. As long as you understand the concept, it's good enough. If you're not familiar with tensor notation, this will be a little bit. But compare this to what I have written in blue. It's pretty much the same thing. It just looks fancier. Right? Now, in linear elastic theory, we only consider this energy density to the second order approximation. We ignore everything above second order. Look here, epsilon times epsilon, epsilon squared. It's second order. Right? If we take only the second order in energy density, we are dealing with linear elastic materials, and that's how we develop linear elastic theory and everything you've seen so far. So these are the notation for a strain. However, in reality, energy density has higher order terms. That's where nonlinearity is coming from. So this part is just saying that the strain relationship, so the strain, when it has two subscripts is a strain, when it has only one is displacement. What we know in linear elastic is this. We normally ignore those higher terms, right? But they exist. Now, Gian, you okay?
Yeah.
Okay. So if we consider the higher term, the expression for energy density becomes like that. Now, the first two terms are second order because you have only two u's. These are now tensors, strain tensors. You only have two multiplied. And for linear elasticity, that's where we stop. We ignore the rest of energy density. You are with me so far? Now, if you write the third order terms, now we are still ignoring the fourth and fifth and sixth, right? If we take into account the third order terms, we can explain acousto-elasticity, and this is what I want to show you. Now, let's focus on this expression for energy density. U here is a strain tensor. If you never heard the word tensor before, it's just a fancy way to for matrix, right? It's a higher dimensional matrices. It just makes things easier in continuum mechanics, the derivations. If you never heard about it, think about it as a matrix, okay? Don't be scared in any ways. I remember the first time in continuum mechanics when I saw it, it kind of was scary, the whole thing. Have you all seen it at some point before? Yes? Yes, 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 yes. Okay. Don't worry. Don't worry. Everyone has seen this for the first time at some point. So the strain tensor is basically, you can think about it, you know, whether you use x or 1, it's the same thing. xx, xy, just as the things you already know. yx, yy. All different components of zx, zy, zz. This is a strain tensor. That's what this bold-faced U is all about, right? T is trace. It's trace of the tensor. Does anyone remember what trace of a matrix or tensor is? What does it mean? Diagonal element. So it is uxx plus uyy plus uzz. If you want to use a fancy something like that. And S is the summation of all over elements. And point is dot product. I have left A, B, and C. What are A, B, and C? Okay, in linear elastic materials, we only have the first two terms. Right? And we only have two elastic parameters. Now, I even brought it with me. I have used the notations from this book, Nonlinear Mesoscopic Elasticity, written by Robert and Paul, whom I have published with both. So I've used these notations. That's why things are a little bit different. I just stayed true to these notations. But shear modulus, they have used mu. It's basically the same as G. But it's good to have seen mu because in a lot of papers and references, this is the notation. Maybe you have seen, especially I think in rock mechanics, people really like to use that. And bulk modulus. So for linear elastic materials, you have to have two parameters, right? Now you have the choice. You can have E and Poisson's ratio. You can have E and G. And one other combination is the so-called Lamb's constants. So you have K and G, right? What is K? It's a bulk modulus. The relationship between K and other parameters, I haven't written it down, but K minus 2G over 3 is the Lamb's constant that I have given you before. So it's another elastic constant. It is basically, if you have hydrostatic pressure, it describes the change in volume due to the hydrostatic pressure. So you can define it. It is defined as change of hydrostatic pressure over relative change in volume. This is volume. Yes. That's how it is defined. And you can show that it's related to Lamb's constant and G the way I showed you before. Some people use lambda and G, but we need two constants. Okay. Everyone is clear with that? We need to go really step by step so I make sure that you are coming with me. Okay. Now, when we go to third order, we need, of course, more parameters to describe the behavior. And those A, B, and C are the so-called third order nonlinear elastic parameters. There are different kinds of nonlinear elastic parameters also in literature. One very important ones are LMN, for example. There is alpha, beta, delta. And if you look in any reference, you can see the relationships between them. I don't know them on top of my head. But you can always look it up. Just know that you need three. And know that why do we call them third order? Why do we call these third order elastic constants? Why? Look at the energy density. Because they describe the third order terms in the energy density expression. That's why. So in comparison, elastic constants are second order. Makes sense? Always remember that. It's a lot of people think elastic constants are first order. No, they're second order because we always refer to energy density. Okay, now we are ready to look at acousto-elasticity. Now, I continue here. You have a, I think you have a blank page maybe afterwards. I continue here. Now, let's look back at the problem that I introduced to you. We have this kind of problem where you are pressing the sample just like we did, and you are measuring p-wave velocity parallel to the sample. How does your strain tensor look like? So we have U sub x. You can use U1 if you want. This is the compressive force that you're applying with your loading machine. A static, quasi-static force. And then we have a strain Ux. How does your strain tensor look like? Assemble your strain tensor for me. Just assemble it. told you what a strain tensor is. We know that we only have compression in one direction, and the deformation, and we have the wave particle velocity also only in that one direction. This is the problem we are tackling. We want to see how the velocity here changes with the strain. This is the question. This is a strain. This is not displacement. So I'm using it for a strain. And you have the wave, the particle strain, let's say the dynamic strain, a small u. Do you agree that we have this at this location and everywhere else we have 0? Right. Now, it's easy now here, for example, to calculate the trace of this tensor. Right. Or the summation of all the elements are also the same. How about this term, summation of u dot q? What would that look like? Exactly. So basically, you can calculate E sub v. If we have for a certain configuration of external quasi-static strain and particle displacement, which also causes a little strain, we can calculate the energy density. Now, the next thing is to use something from continuum mechanics that I write it down, and then let's discuss it. So then we have to calculate sigma. Right. And sigma, once we have the energy density, we just derivative of energy density with respect to ux or the large one, it will be the same, gives us sigma. This is a general assertion. If you want to get sigma here, let's say here, you can use the derivative of EV with respect to epsilon. So from that, we can calculate the relationship for sigma x. I haven't written down what E sub v would be, but you have the expression here. Basically, it will be a function of mu, k, a, b, and c. But if we take the derivative with respect to u sub x, or the large one, this is what we are going to get. So 4/3 of mu, which is g plus k, ux plus 4/3 of mu plus k, small ux, and then 3k 4u mu 2a 6b 2c. Yeah.
So what is this?
This is sigma x. So So now it is not linear anymore, linear elastic. So we have to use the kind of more general expressions. We know how to have the energy density, so this is just the derivative with respect to ux or the large or a small one, because it is symmetric. That a strain tensor is symmetric with respect to the two, so it doesn't matter if we use this or that. So this is what we get. Ux is the quasi-static strain, what we are applying. The small one is because of the propagation of the wave.
So what is the orange sigma x? What's the stress?
That's the total stress. That's the total. Because we have the energy for the total thing. We are just going a step higher. This is not linear elastic anymore. Please ask questions. This is not trivial. I understand. It's a different way. It's not complex really, but it is a more general way. You can use the same thing to get the linear elastic material. So linear elastic properties. So if you ignore all the A terms, A, B, C, you only have this first part. Now, if you look here, if I didn't have A, B, C, and then I didn't have the higher terms, then from this you can basically get the same, and of course then you don't have also ux. This is actually m, this is equal to m. So 4/3 of mu plus k is actually the constraint modulus. So that's basically the linear elastic. Right. Yeah, this is the strain, the derivative of a strain. Yes. Okay. No, this ux is a strain. It's correct. So we have, this is m. This is the constraint modulus. Now, we can divide this into a static and dynamic. So we call this part static and this part dynamic. For obvious reasons, right? So if we take the second derivative of the dynamic stress, we want to get the wave velocity. So the static part doesn't play a role. So we can, basically the rest we have to just deal with the dynamic stress. So the dynamic part would be then m I used x here, we just use the same. M ux plus this expression that you have here. You are all okay with us staying a few minutes longer, finishing this up? Okay, we only are a few minutes away. So this will be the expression that we have. Now, you know that the wave equation, what we are looking at, we want to get the wave equation looked like that. Rho u double dot is equal to the second derivative with respect to x, and we can write this as here. I would have needed an m here. Let's just write the expression with the stress. So I go back to the beginning, to the when we didn't put linear elastic material properties in. So we know that the derivative of a stress is equal to rho times u double dot. This is the first part. And then you substitute for sigma e epsilon. So it's easier to just look at this first expression. So the derivative of sigma x with respect to x is equal to rho u double dot. Okay. So what we need to do is to get the derivative of sigma with respect to x, right? So it would be m I write this maybe derivative of ux. Remember that u was a strain itself, so this u is a little bit different from the u we had before. M, I can write uxx, maybe it's better. But this is a strain itself. So that's why now it is the derivative uxx. And then I write this a little bit differently. So we take 3k plus 4 mu out in a way. And we write the rest like this. I'm just factoring 3k plus 4 mu out. Let me not make a mistake. Ux of course double x. Okay. Let's look. So we calculate sigma x, and then we just focus on the dynamic part of the stress. We say, okay, what we need to establish the wave equation is the derivative of sigma x. So the derivative of sigma x now, it would be just we add here, and you can see where it is going. I want to get m out of it. I want to factor m out, so that's why it is like that. Let me use another color. So now, if we divide this by 3 and multiply it by 3, this 4 mu plus 3k over 3 is m. Correct? I want to basically factor m out. This is the purpose of all of that. So then it becomes m uxx plus m or 3m. I take the m, I can put the 3 inside. M3 plus 3 times this expression. So pay attention that this expression, it is complicated, but it contains only material properties. And we close this uxx. Now, we are almost there. If we divide both sides by density, then this would be equal to u double dot wave equation. Now it's easy to see where we are going. So m over rho is the original velocity squared. right? Velocity 1 is the same as Vp in 3D, and this was m over rho, right? Correct. So I have this velocity. So there is a 1 here, and then this is the same. I'm factoring m over rho out, and let's call this beta. Beta 1. Ux. I'm also factoring out uxx. Okay, we are done. Almost. Now just we have to look at it. Okay. So this is wave equation, isn't it? You have u double dot on one side, and then uxx on the other side. So what relates the derivative with respect to time and with respect to distance is, what is this quantity that I'm looking at? It's the velocity when I have ux squared. So I have a relationship between the second time derivative and second distance derivative. Whatever is relating these two is velocity squared. This is wave equation. So I have now the relationship between velocity under stress and the velocity, the original velocity. I'm there. So the velocity under stress squared is the velocity where there is no stress, the original velocity, times 1 plus some factor times ux. So because the changes are small, we can see that the change in the velocity 1 with respect to the original velocity that we have is actually linearly changing with the string. You know how to get this. You bring this on the other side, divide both sides, and then you say this is a small, and that's what you get. So what I showed you is that if you are pressing a sample along its length and you are measuring the same direction p wave velocity, the velocity is going to change linearly with the string. That's acousto-elasticity. I tried to make this very simple so you can follow me. I hope I was successful. Okay? So that's about it today.